So in this video, I just want to kind of give the basics of P-curvature. It's going to be building towards some other things. So first, let's do a lemma. So let R be a commutative ring, and let's suppose that it has characteristic P. Then what I want to say about this is that the derivations on R, it has the structure of a P-Lie algebra. Okay, and by this we mean that that there's a map where you can take a derivative and send it to another derivative, and to do this you take pth powers. So you compose the map with itself p times. Okay, and the proof of this is very simple. So what you do is you just kind of take a derivation and you apply it to two elements in the ring. Let's say we do it p times here, and then we use the binomial formula to expand this. So this becomes p minus I of f di of g, and since we're working in characteristic p, the binomial coefficients will be divisible by p, and so this just becomes dp here, g plus f dp of g. And so I'm going to write this thing for composed p times, so I'm not going to write the circle always there. And that's the really simple fact there. So why am I doing this? Okay, I'm just going to need that in a bit. So if you haven't seen the video on connections, you should watch the video on connections. Okay, so I'm gonna go a little bit more general now to set up the definition of P-curvature. So we're gonna let X be a scheme over S, and S is gonna be a characteristic P scheme. So this means that P times O of S is equal to 0. And we're going to take an integrable connection. So let's say a locally free sheaf here. And so this is a vector bundle with connection on X, and this is going to be integrable. What integrable means is that so this part here, it means that this connection is going to give us a map from derivations from X over S to endomorphisms, S endomorphisms of E. Okay, so this is a sheaf here, and that furthermore that this thing is going to be a map of Lie algebras. Okay, this integrability thing has nothing to do with characteristic P. This is just in our setup. Okay, so once we have this, what we can do is we can notice that this thing is a P-Lie algebra. Okay, so here, this is a P-Lie algebra. So both of these are P-Lie algebras. Lie algebras. Okay, and so this thing has the pth power map, so you can iterate endomorphisms. And so the question you can ask, so the natural question I'm going to ask is this a morphism of P-Lie algebras? So we have it a morphism of algebras, and it's a morphism of P-Lie algebras. Okay, and because of this leads us to so this brings us to the definition. Of P-curvature. Okay, so with the setup as above, we can make the definition. With the setup as above, and then this thing here we'll define to be, this is equal to the P-curvature, and it's the P-curvature of the connection. And what it does is the following. So for a derivation, we're going to get this guy here applied to the derivation. This is going to be defined to be equal to, well, it's kind of the commutator of the, so it's the commutator of the pth power map. So we can do this to the pth power. We take the connection, so this is the covariant derivative and the pth power minus, now we take the covariant derivative to the pth power. And this thing here is going to be an endomorphism of S modules of E. Okay, so we have this construction here. And so this is the P-curvature. Okay, and so for a derivation, it gives us a new map like so. Okay, so this is what P-curvature is. And now I'm going to talk about some properties of P-curvature. Or maybe I can give an example first. So let me get rid of this here. Okay, maybe I can give an example, and okay, so let x be p1 minus some points, let's say s points, including infinity. So this looks like the affine line, maybe localized at some places. F can be maybe fp. And then we can take our connection to be d, let's say, plus a of t dt. And so this is going to be a matrix with entries in fpt. Okay, and so we'll persist with this example. So this means that the covariant derivative here, it just looks like d dt plus a of t. Okay, and so so this is really corresponds to the differential equation dy dt is equal to, oh, I forgot what to say what bundle this was on. So E in this case, or I did it with a curly E, was O of x to some power. So this is the trivial bundle of rank R. Okay, so then we can have this like vector equation here plus, let's say, a of t y is equal to 0. So again, the connections correspond to differential equations, and this is what we have in this case. And so note that here in this particular case, so d dt, if we do this to the pth power of some guy, let's say t to the m, so t to the m could be an element of O of x. And so this thing again is contained in these things here. So it's like so this is fp of t localized. So this, I mean, this guy here is fp of t localized. So this thing looks like what, m minus 1 all the way up to m minus p, I think plus 1. And then we have t to the m minus p. And so this is going to be equal to 0. Okay? And since it's 0 so this tells us that d dt to the p restricted to fp of t is equal to 0, right? And this will imply that the extension of this derivation to the localization to any localization O of x will also be 0. Okay, and so now what we can do is we can take the P-curvature associated to this connection. So this thing is the commutator of these things to the P like so. And we found out that this one was 0 because this derivative was 0. And then this thing is just going to be minus, and now we write out what it was, d dt plus a of t to the pth power. Okay, so in the most basic case, P-curvature is just this thing, d dt plus a of t raised to some power like so. Okay, and that concludes the example. So again, what was the example? The example was we take x and we localize it at some points here. Okay, so and then what this really does is this makes this sheaf here, really this is just this square sheaf here, but then we localize it at a certain number of points. Okay, so so then when we break down the definition here, what we get is this operator where we've kind of composed our other operator with itself p times. So this normal differential operator here. Okay, and so that's what P-curvature is in the most basic case. Okay, so now I'm going to move to just prove some basic properties of P-curvature. Okay, so I guess we can call this a lemma. And so this is basic properties of P-curvature. Okay, so we're going to let x over s be a scheme. S is going to be as characteristic p. And then we're going to let E nabla be a locally free sheaf with integrable connection. Okay, and what we're going to do is we're going to have P-curvature here, and it's going to be a map from derivations on x over s. And this is the first non-obvious thing that I'm going to say. It says that this endomorphisms of it's actually, so we had it that it was going to be in S linear, but it's actually going to be X linear. Okay, is going to be, let's say, semi-linear. Okay, so this is kind of the first property. Let me say what I mean by this. So this means that for all f and O of x, and all theta 1, theta 2, some derivations on x, we have the following. Let's say, aside this thing here. Okay, this is going to be equal to f to the p, this thing here. Okay, so we're going to have this type of linearity here. So it's going to break up under addition, and then we're going to be able to pull out constants like pth powers. In addition, as elements of let's say S, so let me do it like this, of E, we have the following. So a bunch of things are going to commute. Here, psi theta 0. So these are kind of the basic ones. So these, the proof of this is, these are rather easy. So here theta is a derivation. Okay, so so these are kind of the easier ones. This is this relation here is much more complicated than you'd think. Sorry, maybe I should put squares. I'm trying to put squares here because what you can do is you can actually, to get the actual endomorphism, you can actually apply this again to an E, and that'll be useful later. By an E, I mean an element of this sheaf here. Okay. Okay, so to prove this, so this is kind of tricky. So proving this is kind of trickier than you'd think. This is a little tricky. And let me explain how this works. So to prove it, you need two lemmas. Let's see. Okay. So the proof of the semilinearity needs two lemmas. Okay, so I'm just going to write them as a single lemma. And they're both kind of just silly. So let R be an associative ring of characteristic P. And then there's the following things. So there's the first thing that I need is this Jacobson formula. It says the following. It says that for every A, B, and R, that A plus B to the P is equal to A to the P plus B to the P plus some stuff over here. Okay, and where you have the following, this adjoint action plus B to the P minus 1 applied to A. So these are going to be the universal polynomials here. So 1 to P minus 1 I S I A B T to the I minus 1. Okay, so this is this Jacobson formula, which tells you how to break up Pth powers and how these things are given. And so these are kind of like Lie polynomials. And so these will respect the Lie algebra structure. The second thing that I need, so again, this is all occurring in here. This could be a crazy ring here, potentially. Weird, right? And I'm going to write down the example of the ring that we have in mind. So for all G theta in R, we have the following. G theta to the P is equal to G to the P theta to the P. So it like distributes, but then we have this kind of weird correction factor where you have G, and you have to do the adjoint action P minus 1 times to G to the P minus 1, and then we get theta again. Okay, and so sometimes there's this notation that's used which doesn't refer to theta, but actually involves theta. So Deligne will write it like this. Oh, and I should have said that this formula here is due to Deligne. Okay. All right. So so let me just say some things about the notation here. Some notation. So if we have two things in this ring here, so then the adjoint action of x on y is just this commutator, which is just xy minus yx. Okay, so that's the one of the things that I wanted to say. Then if I wanted to iterate this, so if I do the adjoint action, let me give an example. So if I want to do the adjoint action, say 3 times, so this would be x, let me write it like this. So I'll first do xy, then I'll take the result, do it again, take the result, do it again. Okay? So this is what we mean by this adjoint action when up in this formula here. Okay, and so I said something also about like there's a potentially weird action here. Let me say something about this. So referring back to this point here, so we could take, say, let me go back to black. Okay, so you could say you could take a ring R, and then let's say that it's just any ring. Let's say commutative ring. Let's see. commutative ring. Okay, and then you could take a derivation on R, and then you could make this here. So sometimes people call this script D. This is a non-commutative ring. Oh, non-commutative ring. Of derivations. And okay, so why is this weird? Well, here d times x. Well, you have to actually look at how you, so x you kind of think of as a multiplication operator. So in this ring, this actually becomes x times d plus the derivative applied to x. So for x and r. Okay, so this is how you commute these two things. And so you kind of view as x as a multiplication by x operator. And under this viewpoint here, well, we can write this d dot x plus x dot d. So this becomes xd plus this thing here minus xd. Okay, so I just wrote out this one out here. And this just becomes the derivative of x. Okay, so when you're working in these non-commutative rings, you have to keep this type of thing in mind, so that if you act by a derivative operator in something like this, so this is a general non-commutative ring. So okay, and then here I've fixed it to be commutative. So actually this R. So this is like that script D that I did before. Okay. So yeah. So that's that. Okay. So I'm just going to make some remarks for Deligne's formula. So I gave the proof of Jacobson's formula in another video. Deligne's formula. The idea is to. This is Deligne's formula. So you reduce to a general expression for, I mean, so you're kind of just going to compute something stronger for g theta to the n. And then this thing certainly relies on it being characteristic P. Okay, I guess they both do. Yeah, and so, and then you prove something about the coefficients in the formula, and I'll link to so you show like essentially most of the coefficients are 0 in the formula that you get here. And I'll link to where the proof is. Okay. So, so that being said, I'm going to now prove the linearity for the P-curvature. My notes aren't loading. 1 second.